The broadcast is now starting. All attendees are in listen-only mode.
Good morning. My name is Gary Corley with Kirby Smith Machinery. I want to welcome you to our third webinar promoting training and quality for the asphalt paving industry. I will serve as your moderator this morning. We are producing this series in conjunction with our friends and partners with the working group, which includes Hum Compactors and Bogley Pavers. Today's topic is basic asphalt paving, which we will follow with an advanced paving webinar at a later date. Our presenter today is the Bogley Paving Products Manager, Nars Narsingh. Nars is a 25-year veteran of the asphalt paving industry and has a wealth of knowledge on the topic. I know you will enjoy his remarks this morning. During today's presentation, if you should have a question, you can pose that question over in the chat box on the right-hand side of your screen. I, in turn, will pose the question to Nars, and we'll do our best to get you a good answer. Without any hesitation, Nars, if you're ready, I'll turn the broadcast over to you.
Okay, Gary, thank you very much, and welcome everyone. Our topic today is Paving 101, which is basic paving. I'll start with explaining the principles of the free-floating screed. What are some of the forces acting on the screed to hold it to grade? What are some of the issues affecting each of the forces holding the screed to grade and its impact on smoothness and density? We will also look at the importance of screed adjustments impacting angle of attack, strike off, strike to a point position, and what it takes or what are all the adjustments required to pull off the joint. And we will also look at the different type of screeds out there and apply the basic principles to each of these screed concepts to show how smoothness and density are getting impacted. So let's first start with taking a look at a very simple side view of an asphalt screed. As you can see there in white, black outline is the side view of the main screed, and we will keep it simple for now, only showing one screed section. You could also see the augers in black and the head of material in front of the screed in gray. Now, at the front of the screed, which we refer to as the leading edge of the screed plate, and at the back of the screed is what we refer to as the trailing edge of the screed plate. And these are two terminologies we'll be using very frequently in the next 45 minutes. So let's take another look at the side view, but now let's look at our different compaction levels at the screed. At the leading edge, which is the shear point, that's the first point of contact with the head of material as the screed moves forward, you have zero compaction. And then, of course, the trailing edge, which should be the last point of the screed plate contacting the material, is where you have your max screed compaction. The angle that you see there is what is referred to as the screed angle of attack. One should know that when a screed is paving for proper performance, the screed should not be sitting flat. If it's a vibratory screed, it needs to have an angle of attack. And again, that's another terminology we will be using very frequently in the next 45 minutes. Now, keeping this real simple, let's assume that the leading edge of the screed plate is plane A, and the trailing edge of the screed plate is plane B. So the difference in height between plane A and plane B is what is referred to as your screed compaction. And that leads to the angle that refers to as the angle of attack. Okay. Now let's take that one step further, because we know all screed plate have a radius in the front and it's not pointed as you see here. So in front of the radius of the screed plate is your main strike-off. So your main strike-off determines the amount of material flowing under the screed plate, or it meters the amount of material flowing under the screed plate. As the material hits that radius point, it will start to compact from your strike off to the flat portion of the screed plate. That compaction is referred to as your extrusion compaction, as you can see it here. So the first compaction as the asphalt flow through the radius of the screed plate is referred to as your extrusion compaction. As the screed moves forwards, the asphalt would have to be compacted from that point to that point due to the angle of attack of the screed plate. That is referred to as the gradient compaction. And of course, we also have compaction due to vibration. So those are the different forms of compaction that occurs under the vibratory screed. Okay, let's take a look at the paver now. Remember, this is Paving 101, so we're keeping this simple. You could see the tractor and the screed. So a paver consists of a tractor and a screed. The screed is connected to the tractor by the screed leveling arm. Some call it tow arm, some call it leveling arm. The leveling arm is connected to the screed via the screed arm. So the screed arm is bolted to the leveling arm. Now, to give you a better visual, let's look at a line diagram of the tractor and the screed. And let's get familiar with some of the key components of the asphalt paver. So we have the tractor in green, and we have the screed in white. We have the screed arm that connects the screed at the pivot point. So the pivot point is a point at which the screed rotates as one turns the thickness control screws. So turning the screws clockwise in some cases, counterclockwise in some cases, will allow the screed to rotate to increase or decrease this equilibrium angle of attack. And we'll come back to that. So the screed arm is connected to the tow arm, and the tow arm is attached or is being pulled by the tractor at the tow point. Okay? So here is your paver, your tractor, which has the hopper that receives the asphalt, whether it's being dumped into by a truck or fed by a material transfer vehicle. So the asphalt comes into the hopper. There's two slot conveyors that drags the mix to the back and delivers it into what we refer to as the auger chambers, and then the auger spreads the mix across in front of the screed. Okay? So those are some of the key components of the asphalt paver. Now, I will try to keep this simple by removing the tractor and just keeping the screed. So if you look at the next drawing, you see there is the screed and the tractor is removed. So once again, referring to the key components, you have the leveling arm, you have the screed arm, you have your thickness control screws, of course your angle of attack, and this is referred to as your tow point cylinder. So this will move up and down, looking at the green arrow. Your thickness control screws, as you turn it, the screed rotates about that pivot point. So now let's take a look at how we increase mat depth after equilibrium point using the thickness control screws. So at the equilibrium, we're paving along, we're holding 1.5 inch mat depth. Now we need to change our mat to, let's say, 1.75 inches. So one will turn the screw, whether it's clockwise or counterclockwise, depending on whose paver it is, to rotate this entire mass about that pivot point to increase that angle of attack. So that angle will now be at the greater point. By doing that, more asphalt is allowed to flow under the screed plate. Asphalt acts like liquid. There is only so much you can compact it. So as more asphalt flows under the screed plate, it will force the screed up to give it a thicker mat. Likewise, you turn the screw in an opposite direction, and that will reduce the angle of attack momentarily, allowing less asphalt to flow under the screed, and the screed will drop to give you a thinner mat. Now, we could accomplish all of that by leaving the screws alone and just use the tow point jog switch to move the pull point up and down to increase or decrease that angle of attack, to increase or decrease your mat depth. That's the manual way using the jog switch. The screw is the manual way using, of course, the thickness control screws. Now, we could leave all of this together and we could use an automatic grade and slope system using a reference point to automatically control the angle of attack, to control your mat depth. Now, we will not get involved in that discussion today. That will be later on for the advanced paving. So manually increasing or decreasing the mat depth is done by using your thickness control screws or your tool point. Now, once you increase that angle of attack and the screed starts to raise, then this entire mass, screed arm, toe arm, and screed locked together, rotates above to increase the mat depth, but it's rotating about this point here. So asphalt flows under the screed, pushes the screed up, the entire mass rotate about that point to give you a thicker mat, or rotate downwards to give you a thinner mat. That process does not happen instantly. That process takes 3 to 5 times the length of the toe arm. So when you make a change, whether it's with the thickness control screws or the toe point, the time it takes is 3 to 5 times the length of the toe arm. The first length, however, roughly 65% of the changes occur. And then about the third length, 85%, and then finally about the fifth length, 100%. Now, for different screeds, that may be 3 to 5 lengths, so a lighter screed will respond quicker than a heavier screed. That's one of the reasons why a heavier screed is more suited for mainline paving, and a lighter screed is more suited for commercial type paving, where you're constantly making changes and looking for quick response. And we'll get back to this discussion later. So remember, from the time we make the change, the entire mass rotates about that point to give you a thicker mat or to give you a thinner mat. That process takes 3 to 5 times the length of the toe arm, so it does not happen instantly. So whenever you make a change, give the screed enough time to react before you check your mat depth. Also, know your subgrade. If it's smooth, you check it once, then you should be good. If you know there is an irregular subbase, then you need to check it a few times, but not constantly as seen on this picture here. You can see where the paver was pulled off in a joint, and you can see every foot one was poking in the mat trying to get the mat depth. So you have to give this screed time to react, to get to grade before you check the mat depth. Okay. Now, let's look at how the free-floating screed works on an irregular subgrade. Knowing now how we increase angle of attack, how we increase mat depth, let's look at a subgrade with short undulation, say 15, 20 inches. For better visual, let's take a look at a wheel paver. So as the front wheel goes into that short undulation, of course, your toe point will try to drop. Your toe point will get thinner, so the angle of attack will reduce momentarily. But because it's only a short undulation, there's not enough time for the screed to react, so it fills that low point. Likewise, for a high point, as the wheel goes over that high point, the toe point position will go up, increasing your angle of attack. But because, again, it's a short irregularity, it's not 3 to 5 times the length of the toe arm, there will be no change. However, if it's a long undulation, 20, 30 feet long, as the tractor follows that undulation, the toe point will follow accordingly, and the mat depth will follow accordingly because it's now much longer than 3 to 5 times the length of the toe arm. So the swale or the valley in the subgrade will be followed by the asphalt. Now, this is one of the reasons why we use averaging ski if you want to fill that long swale or long undulation. So the averaging ski bridge that gap, and your automatic grade and slope system follows it to give you or to fill the low spot, as you could see here. So a long averaging beam, and they could be anywhere from 20 feet to 60 feet. I've seen cases where a beam is as long as 60 feet. In the old days, they have mechanical skis that are being dragged along the road, so it bridged that gap with the automatic grade and slope system, following the ski and automatically controlling the toe point cylinder to increase or decrease the mat depth. Again, you could see another form of mechanical ski. And the newer versions today are non-contact averaging ski, but the accuracy is pretty much the same, irrespective of which of the two. But this discussion will be again in details with the advanced paving seminar. Now, that's how the asphalt free-floating screed work. Now let's take a look at what holds the screed in grade, or the equilibrium position that we talked about, or the equilibrium angle of attack position. There's no mechanical grade, not like a concrete paver or a milling machine. There's no mechanical lock, there's no hydraulic lock. The screed is free flowing, and the side forces that holds the screed in grade. What are some of the things that we do on the job site that makes these 5 forces vary? Five forces act on the screed to hold different point positions for adjustment. An equilibrium angle of attack, which we refer to as angle of attack. Any change in the 5 forces causes screed to raise and fall. So, Kelsey?
NARS, it's Gary Corley. I believe we're having some difficulty with your Wi-Fi connection.
Yes.
I think what we would be better doing, better served doing, is playing the recording we did at a practice session that we did earlier. So if you find folks in the audience, if you will bear with us for just a moment, we'll bring up that recording, and it will be the same product, the same training, same everything. We'll just begin at the beginning and go through the entire process. The only addition, the only negative about that is that you will not be able to pose real-time questions. So, but feel free to contact me with any questions that you have. That my email address will be noted on the recording that we're about to break to. So, Madam Producer, if you want to begin the recording. Basic asphalt paving, which we will follow with an additional webinar on advanced paving at a later date. Our presenter today is the Mobley Paving Products Manager, NARS Narsing. NARS has a wealth of information in the asphalt paving business as well, and is very well respected in the industry. I'm sure you'll enjoy his presentation this morning. During today's presentation, if you have any questions, you can post them in the chat portion of the screen on the right-hand side, and I in turn will pose those questions to NARS and get you an answer. So without any further ado, NARS, if you are ready to proceed, I'll turn it over to you.
Okay, Gary, thank you very much. Today's topic would be Paving 101. So we will discuss the basic principles of the free-floating screed, how the free-floating screed function, and what are the things that impact the free-floating screed on the day-to-day operation while paving. So we will start with taking a quick view of the screed looking from the side. As you can see there, we have the leading edge of the screed, which at that point there is zero compaction. And then you have the trailing edge of the screed, which is, Gary, can you see my mouse? Kelsey?
Yes, I can see it.
Okay. The trailing edge of the screed is where you have maximum screed compaction. The distance in height between plane A and plane B is your angle of attack, which is your screed compaction. So that's looking at a simple side view of the screed. Now we can take it a little bit more complicated and add the bullnose or the radius of the screed blade. And every screed in North America have a bullnose or a radius. Exception of CAT, rear mount screed that has a machine profile that takes the shape of the bullnose. So you can see there now in adding the bullnose, there's 3 forms of compaction on the vibratory screed. You have, at the front of the screed plate, you have your extrusion compaction, which is as the material flows over the radius of the screed plate. Then you have your gradient compaction. As the screed moves forwards, the material compacts due to the angle of attack of the screed. And of course you have your vibration compaction, which is from the vibration system. Taking a quick review of the paver, you have a tractor and a screed, where the tractor pulls the screed and it receives the material from the delivery equipment, whether it's a truck or a material transfer vehicle, and it delivers the asphalt to the screed. So looking at some key components of the paver, we start with the tractor, and you have your toe point cylinder, which moves the toe point or the screed arm up and down. You have your leveling arm, which connects the screed to the tractor, and you have your screed arm, which allows the screed to pivot, meaning it could rotate at the pivot point, which is connected to the screed arm. You have your thickness control screws. As you turn the screw clockwise or counterclockwise, depending on whose screed you have, the leading edge of the screed will increase or decrease to increase or decrease your angle of attack. Then you have your toe point, which is a point of contact, this leveling arm and the tractor. So whilst paving, you have what we call an equilibrium angle of attack. At the equilibrium point, we have a consistent mat depth. And again, the mat depth is determined by the trailing edge of the screed plate. So these are all some of the key components of the paver and the screed. Now let's take a look at the screed alone, leaving the tractor out for simplicity. We have the toe point cylinder with a green arrow next to it, and we have the thickness control screw, and again we're showing the angle of attack. So how do we increase or decrease mat depth? We increase or decrease mat depth by turning the screw to increase the angle of attack. As we turn the screw, the screed pivots about the pivot point, roll backwards to increase the angle. As we increase the angle, more material flows under the screed, and it acts like water or fluid, which means the more material flows under the screed, with the given compaction, the screed will be forced to raise, giving a thicker mat. To get a thinner mat, you turn the screw in the opposite direction to momentarily reduce the angle of attack. Less material flows under the screed to give you a thinner mat. So that's how we increase the mat depth using the thickness control screws. Now, if we were to leave the screws alone and we use a toe point, we could manually raise the screed arm to achieve the same thing as rotating the screws. So if we move the toe point up, we will increase the angle of attack of the screed, allowing more asphalt to flow under the screed, pushing it up to give a thicker mat. Or we move the toe point down, decrease the angle, allowing less material to flow under the screed, and hence reduce the mat depth. So that's a manual way using the screw or using the toe point. once we make that change, it takes time for the asphalt to get under the screed, pushes the screed up to get it back to the equilibrium angle of attack that we talked about earlier. That is usually 3 to 5 times the length of the toe arm. So that means a heavier screed will take longer to get to that equilibrium point. A lighter screed will be quicker in reaching the equilibrium. So generally, most operators prefer a lighter screed for commercial type work where you're looking for quick response to the screed, and a heavier screed for mainline work where you're looking for more stability and smoothness. So once you set your mat depth, it's always wise to allow the screed to float freely rather than constantly changing your screw position back and forth or your toe point position back and forth because of the time it takes for the screed to reach equilibrium. Also, once you make a change, of course you need to give it time to reach that equilibrium point. So when you're checking your mat depth, don't check right after you make a change. Give the screed some time to reach that equilibrium point, and also know what your subbase is like, whether it's smooth or it's have undulations on it. So we can explain all of this with showing a picture of a mat. As you can see there, these are constant checking of the mat depth every 6 inches every foot. Putting holes in a mat when it's absolutely not necessary. So you always have to give the screed time to get to its equilibrium point before you check the mat depth. So let's look at how the free-floating screed work again. We said it takes 3 to 5 times the length of the toe arm to meet that equilibrium point. So assuming we have a subgrade with multiple undulations on it, some short, some long. And for simplicity or a better visual, let's assume we're using a rubber tire. So as the front wheel goes into this short undulation, of course the toe point position will go down, which means the screed would want to change grade. But because the undulations is so short, it's not even close to half the time the length of the toe arm, so the screed will not respond. Instead, it will float over that undulation to hold a flat surface. Now, if we're going into a long undulation, longer than the length of the track or the wheelbase, then of course the toe point will follow the wheel and the mat depth will follow accordingly. So here it will fill the hole or shave the high spot. Here it would follow. So this is a classic case where one will use an averaging ski to bridge this longer undulation and let the toe point follow a ski using automation system to fill that long undulation. So we can summarize all of this with a short video. Of course it's not working, so I got to find that out. Now you can see here a high spot and a low spot. And here's an averaging ski, which is a mechanical ski that bridged that low spot, and with the automation system, the screed was able to keep a flat plane to maintain smoothness. Now, you can see another view of a mechanical ski that's being pulled by the paver. Most current technology is non-contact averaging ski, where there are multiple sensors measuring the depth of the subgrade to give an average, as opposed to dragging a contact ski, which is usually very tedious at intersections and areas where you need to or not need to use a ski. So skis are used to fill those long undulations when you have uneven subgrade. So that's basically how the free-floating screed works. Now, what keeps the screed to equilibrium point? The screed is held in equilibrium by 5 forces. there is no mechanical lock or hydraulic lock that holds the screed to grade. It's held to grade by 5 forces acting on the screed. So today we will review each of those 5 forces and look at how we could control each of these forces whilst we're paving. So we could look at each of these one by one, and then we will look at each of the forces and see how we could maintain consistency whilst we're paving. Now, the first force is what we refer to as the pull force. That's the force exerted by the tractor to pull the screed. Then the second is the amount of asphalt sitting in front of the screed. That's called gross material. That creates a resistance to movement. And then you have the weight of the screed, which of course we can't change on the job site. That's by design. And the last two is the reaction force, which is the ability of the material to keep the screed in suspension. And then we have the frictional resistance of the material as it flows under the screed bed. So when these 5 forces are in balance, the screed will hold grade. So at equilibrium, all the forces are in balance. Constant mat depth is maintained. The screed is free-floating with an equilibrium angle of attack. That's the angle of attack you can see there. Change in any of the 5 forces causes the screed to raise or fall. So the objective is for consistent mat smoothness is to maintain consistency on each of these 5 forces. So let's look at each one by one. So starting with the pull force. Of course, speeding up and slowing down disrupt the equilibrium of forces. Changes in resistance of the screed against the head of material, resulting in change in the mat thickness and eventually a rough ride. So the objective of the operator is to pick a consistent speed based on the amount of mix that could be delivered to the job site, not the plant capacity, but not only the plant capacity, but also trucking, traffic in the way, and all those other stuff that will determine how often a truck could get to the job site. So once that is determined, knowing your paving width and your paving depth, you could determine your paving speed. So once the speed is determined, the operator usually in most pavers today have a speed dial where he could set his speed so he knows how far he's going. In our case, we give the operator a dial and we give him a display so he can set his speed whilst he's sitting so he knows how fast he's going. So these are some of the features that we added to the paver to make the operator life much easier. So as we said, maintain a consistent paving speed as possible. Plan the job. Paving speed should be based on material delivery and also rolling capabilities. Tonnage delivered equals to tonnage laid. So tonnage laid equals to the max paving speed times the mat depth times the mat thickness. And there are several different calculators out there that one can use to make this calculation much easier. Now let's look at some of the things that happens when we disrupt the pull force. As we know, the screed's got weight. The asphalt is soft, so every time you stop, the screed will settle. And if you follow this point here being fixed, as the screed settles, it's rotating downwards, and as it rotates with that point being fixed, the angle of attack will change. The angle of attack will increase. So when you take off, you're now taking off with a steeper angle of attack compared to when you stop. So that means the mat in front of the point at which you stop will be thicker than before you stop. Also, you will have a settling point. Now, all screed does this. Some are worse than others. The heavier the screed, the worse it is. So one of the features that we have added to our paver, and some other pavers have this feature as an option, is when you stop, the screed goes into a hydraulic lock. So it prevents it from settling. And when you take off, it stayed at that position for 4 seconds or 18 inches, whichever comes first, to prevent the hump in front of the screed. So that feature prevents any settling or any hump in front of the screed to maximize your smoothness. As you can see here, see the settle point, and then you see the hump in front of the screed. Now, the main reason why we use material transfer vehicles is to minimize that hump. And to prevent the truck from bumping into paper to allow for non-contact continuous paving. So material transfer vehicles were basically introduced for non-contact continuous paving. Don't stop, don't bump the pavement. And these are some of the different types of material transfer vehicles that are used out there today. And again, basically is to maintain consistent pull force, which is the first force that we started talking about. Also, one of the most important things that one needs to follow whilst paving is to maintain that consistent pull force is to follow a string line, something that the operator could follow to keep a straight line. And most importantly, going into a radius. So most pavers, especially track pavers today, it's very difficult to hold that smooth radius. And if you're jogging through the radius, the screed will be moving side to side, disrupting the five forces in equilibrium, and produce a rough ride into the turn. So most operators today should have their foreman provide a steering guide for them to follow to be able to achieve a straight line and maintain consistency in the pull force. So let's look at the head of material now. That's the second force we talked about. So one of the most important things for operators is to maintain a consistent head of material. Most pavers today have the features that allows them to do that. The older pavers today uses flow gates to regulate the amount of mix that delivers to the augers. Today's paver have independent augers and conveyors, so the operator has the ability to set the speed of the conveyor and the augers to maintain that consistent head of material. We took it to an additional level, and we allow you to use an independent control at the rear of the conveyor rather than a flow gate in front of the conveyor. They both do the same thing. They allow the operator to regulate the height of the material in front of the tunnel, and with the auger sensors, regulate the height of the material out of the end. So these sensors should be set such that the amount of mix being laid equals to the amount of mix being delivered by the conveyors, with a consistent head from the center all the way out to the end. And you can see what consistency look like here. Just a continuous movement of the augers delivering consistent flow. That's it. Okay. So we also give the operator the ability to visualize how much asphalt is in front of the tunnel by using these two digital displays that's being controlled by the two paddles in front of the tunnel. So the operator could monitor the amount of mix in front of the screen by just looking at these displays rather than constantly bend over to look into the auger chamber. We also give the operator the ability to, in case of failed sensors, to go into the screed control and set his auger and conveyor to whatever RPM is desired based on his paving speed and his paving width. So he could go into the screed control, and he could set his conveyor and augers in terms of, in case of failures. Here you could set your augers to whatever RPM is required, and here you could set your conveyors to whatever RPM is required. So in case of failures, you could still maintain consistency in your head of material. So that's your second force. Now we could look at the third force, which is the weight of the screed, but we all know the weight of the screed is by design and usually cannot be changed on the job site. However, we should realize that the heavier the screed is, the less reaction you will have to changes in the other four forces that are beyond our control. So a heavier screed is more suited where you're trying to achieve maximum smoothness. A lighter screed is better when you're doing commercial type work where smoothness is not that critical, but versatility is more critical. The challenge we have is one cannot design one screed as best for all applications. So today most contractors try to find a screed that's okay for all the different type of applications that he's involved in. The last two forces, the reaction force and the frictional force. If you look at the things that impact the reaction force, it's the asphalt content, the temperature variation, and the gradation consistency. Now, these are things that one would say cannot be changed on the job site. But before we get into the details, let's look at the last force. Again, you will see the things that affect the frictional forces, the asphalt content, the temperature variation, and gradation consistency, which is common with reaction force. But also some things that affect the frictional forces, the extension screed angle of attack, the vertical position of the extension screed relative to the main screed, strike compensation, screed line of flow, which are all basically adjustments. So for the last two forces, we could break it down as controlling or maximizing your adjustments and controlling your mix consistency. So we could say that mix consistency could be affected on the job site if one segregate the material. So segregation will impact the asphalt content. Segregation will impact the temperature variation, and also segregation will impact the gradation consistency. So the objective is to prevent any segregation possible from going under the screed. And that's another reason why we use material transfer vehicles and some sort of a remixing device either in the paver or in the material transfer vehicle to ensure material consistency. But we will leave segregation discussion for the advanced part of this program. And today we will just look at the proper adjustment of the screed so we can control the frictional force. So coming back to the simple side view of the asphalt of the screed, again we see the angle of attack, mat thickness, screed compaction due to the angle of attack, material falling under the screed. So the shear point of the asphalt is at the leading edge, and your final compaction point is at the trailing edge. So right off the bat, looking at the trailing edge, if you get out on the job site, you can see daylight between the trailing edge and the mat surface. Then right off the bat, you should be able to tell that something is not right, because the trailing edge should be the last thing to attack the asphalt. So the difference in height between the leading edge and the trailing edge is your screed compaction. Now, we know that we have multiple screed sections. So looking at an extendable screed with a rear mount screed, you have your main screed in the front and your extension is at the back. However, for consistent density, all leading edge of the screed must be on the same plane between the left-hand extension, right-hand extension, and the main screed. And all the trailing edges also must be on the same plane. So the shear point on the main screed is the same as the shear point on the extension. The final compaction point on the main, which is the trailing edge, should be the same height as the extension screed. So whether it's a front mount screed or a rear mount screed, it does not matter. The principle is still the same. All leading edges must be on the same plane, and all trailing edges must be on the same plane. So VA, or vertical adjust, or match height, referred to by some, allows the operator to position the trailing edge of the extension screed relative to the trailing edge of the main screed. So with your match height, you could move the extension up and down to allow the trailing edge to be on the same plane of the main screed. Extension independent angle of attack allows the leading edge of the extension screed, whether it's an unequal width screed like we see over here, which is like a Carlson screed or Blonox Ultimate or Cedar Rapids Stretch 20, or several different types of unequal width screeds out there. So the extension independent angle of attack allows the operator to rotate the extension screed and allow the leading edge to be on the same plane as the main screed. For equal width screeds, the angle of attack changes with the main screed, so there is no external adjustment that can be done on the fly with equal width front mount screeds. Unequal width front mount screeds have an additional adjustment that allows the operator to position the leading edge on the same plane as the main screed. So one of the secret of a good screed adjustment is rigidity. The support structure for the main screed, for the extension screed, needs to be rigid to hold those adjustments, whether you're paving 10 feet, 12, 14, 16, 20, or even up to 28 feet wide. So the objective is to always hold that position from one end of the screed to the other end, allowing this distance to be consistent from one end meter to the other. Now, if all the adjustments is correct, of course you will have consistent density, consistent surface texture, and you will have a mat that looks like it should. In this case, if you have the leading edge of the extension higher than the main, that much more asphalt will flow under the extension screed, allowing more compaction under the extension, less compaction on the main. So the main will be more fluffed, and your in-place density will be less. So after it's rolled, you will have a lower surface here than you will have in the areas where you have higher in-place density, as you can see here. That's higher in-place density. You could see the dragging and the pulling here. That's less compaction. So of course, when the roller comes along, your final compaction or that final surface will be lower than that surface there. And of course, your smoothness will not be achieved. And you can have several different adjustments. That's not correct. Here you can see the extension is compacting more than the main, so you have less compaction here. Here you hardly have any compaction under the extensions. And of course, here you have more compaction under the extension, less on the main. And over here, that's what it needs to be. So those are extensions of the adjustments of the extension screed relative to the main screed. Now we also have a main strike-off on every screed in the U.S. which meters the amount of asphalt that flows under the screed. And that metering device, which is called a strike-off, is adjustable. So usually the adjustment position is the bottom of the strike-off. It's usually half inch above the screed. Now you can see here, if the strike-off is too low, when you take off, the screed will try to nosedive, and of course the operator will turn his screw or move his toe point up to significantly increase his angle of attack to whole grade, which will put more pressure on the trailing edge of the screed plate, which will provide several disadvantages when stopped, excessive wear on the trailing edge of the screed plate and all those stuff that are not good. On the other hand, if the strike-off is too high, when you take off, the screed will tend to climb, giving a thicker mat, and of course the operator will turn his screw in the opposite direction to bring the screed on its nose to hold depth, putting the trailing edge off the mat, which again is not good. So that's your strike-off adjustment. Now, line of pull is pretty critical. Is where do you position the toe point, depending on your mat depth. It's usually positioned in line with the pivot point of the screed. So you don't want the toe point to be high, or you don't want the toe point to be too low. If your toe point is too low, just like the strike-off, the screed will be riding on its nose, on its tail, increasing the wear on the trailing edge, and also when you stop, increasing the settling and the hum in front of the screed when you take off. If the toe point is too high, the screed will be riding on its nose, and it will not be free-floating. So, how do we take off? When sitting at a joint, what are all the right things to do before we take off? So first thing is you determine the thickness of the mat and determine the thickness of the starting blocks. Lower the screed on the starting block, pull forward at least 1.5 inches to take up any slack between the pull point and the pull bracket. Lower the augers approximately 2 inches above the screed plate. So the thicker you pave, the higher the augers will go. Position the toe point in line with the pivot point of the screed. On some screed, you need to energize the screed float switch to allow the screed to go into float mode. Null the screws, which means you allow the screed to sit flat on your takeoff block. then take up the slack with your screws, add 2 to 3 turns depending on your map depth and your mix design, which one should know from experience. Fill the auger chambers and then take off. So this is generally basic rule of thumb for taking off from sitting at the joint. And if this practice is followed, you could turn your automation on and pull off, leaving a proper joint. So those are some of the things.
Darsh,
Yes.
Quick question. Could you speak to the importance of having an appropriate amount of material in the hopper and in the augers at that moment? I've seen a number of cases where the material the screed will be starved, and it creates a need for a lot of hand work.
Right.
Would you address that?
Yeah. If we
Thank you.
we said that segregation is one of the most important things that will change the asphalt content, change the asphalt gradation. So if we have a half-filled hopper and we have segregated mix in the hopper flowing under the screed, then the consistency of the mix at the point of pull-off will be completely different from the consistency of the mix as we move forward. That means the angle of attack will change because the interlock of the aggregate will be different because we have a different gradation as we take off. So it's always wise to have a full hopper and your screed loaded to half the auger shaft. So proper paving practice is covering half the auger shaft and maintain that at all times while paving. So if the augers is positioned 2 inches above the screed plate and the augers are half covered and there is no segregated mix under the screed, following these procedures, you should be able to take off and not have to spend too much time at the joint finishing your prep. Okay? So now that we understand the basic principles of the free-floating screed, we'll wrap up by looking at the different type of screeds out there and what are some of the advantages and disadvantages based on what we have just learned. So this is basically the original free-floating screed. It was usually referred to as a wedge lock screed. Only the main screed will provide compaction. The extension was just a hydraulic strike-off, leaving a fluff, which is usually knocked down by the rotor. So those screeds were not used on mainline work unless they had hard bolt-on extensions onto the main screed. So those screeds have evolved now to what we refer to as full hydraulic extended screed. Here we could see a rear mount version where the extension is at the back of the main screed. Here is a front mount equal width version where the extension is in front of the main screed. And here is an unequal width front mount. Unequal means the extension is narrower than the main, as you can see. In all 3 cases, we're paving in this direction. So what are some of the advantages and disadvantages? As we look at this screed here, you can see a pocket of mix between the end gate and the main screed. So if we're paving along and we have storm sewers, manholes, any kinds of restrictions that's sitting in front of the path of paving, as we approach those, we will have to reduce the head of material to get that end gate in. Or we'll have to get right up to the obstruction, stop, and shovel that mix out to get the end gate in. So the 2 things that we've done is opposite to what we talked about earlier, is to maintain a consistent mix, stop as minimum as possible. So these types of screed are usually not the best for jobs where you're doing constant, where you're paving and have constant obstructions in the path. Also, you have a very long end gate in this case, so whatever obstructions you have, as you get past it, you pull your screed in, you go past and then pull it back out. You usually have to wait the length of the end gate minimum, which leaves a lot of handwork. Now, if you look at the equal width front mount screed, you have this pocket of material now sits in the middle of the screed. It's even more challenging to get to that mix to shovel it out if you have to, because if that pocket is filled with mix and you try to bring that extension back in, of course, it will be difficult to do. So in this case, you will be forced to raise the screed, get it in, move forward, lower it again, and start all over again, which is a lot of handwork, takes a lot of time. And also you have a strike off in the middle that regulates the mix in between the extensions. Those strike offs are usually the first thing that finds the manhole or storm sewer or whatever obstructions you have in front of you. So there is disadvantage there, but the advantage is that a short end gate, so any obstructions you have less hand work as you pull your screed. Now the most recent screed design is what we refer to as unequal with front end screeds. Because the extension is narrow, it does not need or require the strike off to regulate the amount of mix in the center. And most good designs today have a tapered interface. So you could go from fully extended to fully retracted, and these two tapered face pushes material forward, allowing the extension to easily retract from fully extended position to fully retract position without even slowing down or stopping. The disadvantage here is, as we said earlier, you have one additional adjustment to make with these screeds because it's different width. You have to use the extension independent angle of attack adjustment to allow you to position in the leading edge of the extension to the same plane. The advantage is you could pave around obstructions without slowing down, without stopping, without disrupting the flow of mix, and it's usually more versatile for jobs where you need to consistently go in and out. They're also good enough for all mainline work if it's heavy enough and if the extension support structure is rigid enough. So today's design are getting even closer to being as rigid as these main rear mount screeds, and the mat quality are as good as these rear mount screeds or these equal width screeds, except require one additional adjustment. So most contractors today are using these type of screeds mainly because of its versatility. And we can see here one of the obstructions we're talking about. You can come right up to it, pull forward, and go. Or it's consistent flow of material. And in this case, you could see trying to get that extension back in against that main screed would be pretty challenging. Again, you can see what happens to the head of material. There it is as we're trying to retract, and there it is trying to get all the way in. So that's where the head of material was, that's where it is now. So force number 2 that we talked about earlier was to maintain consistency. Here we have significantly changed. So if the operator does not compensate with his screw to maintain his mat grade, of course the mat depth will change as we bring the screed in to dodge whatever obstructions. Once again, these are the different types of screeds. There is a strike off in front of the equal with front mount screeds, as you can see right here. There is the unequal width screed looking from the bottom. There is a taper face that allows the mix to push forward rather than getting trapped. There is another version of an unequal width screed with no taper. It makes it very challenging as you try to retract. As you can see there, the extension is in front of the main, so you can bring that extension all the way in without dropping any material. So that's as far as we would like to cover with Paving 101. And next week we will be doing the advanced paving, where we will be covering segregation and longitudinal joints and automatic exhausts, and some of the other things that we don't have time to cover today. So ladies and gentlemen, thank you very much. And I turn this back over to Kirby Smith.
Nurse, thank you very much for the most informative session this morning. If you have any questions about today's presentation, I can be reached at gcorley@kirby-smith.com. And just like our 2 compaction webinars, excuse me, today's presentation will be posted at our Kirby Smith website, so that you can use these at your leisure. Our advanced paving seminar date will be announced via e-blast and posted on our website. You'll want to register early for this, as our enrollment in each one of these webinars has been increasing. And along those lines, I would love to hear from you with any suggestions that you might have to help improve our presentations or make them more user friendly. This has been a very enjoyable experience for all of us here at Kirby Smith. It's good to be with you this morning. Thanks for your attention. Be safe on the road, safe on the job.